Welcome back. In this session, we'll learn one important shift of a sequence that's referred as circular shift. Let's start. So, before we learn what do we mean by a circular shift, let's suppose we have a sequence x of n, that is n point sequence, like this is x of n minus 1, right? So, this is our n point sequence. So, this is the n point sequence. In other words, we say x of n is represented by these n points. So, I mean, this is n equal to 0 point, this is n equal to 1, this is n equal to 2, so on. This is n equal to n minus 1 of n. Or in other words, the limit or the duration of the sequence varies from 0 to n minus 1, and that form is equal to the n points of this sequence. We say this sequence is completely represented by these n points. All right, and we say this is a causal signal that I told you already earlier. That means the negative part of the sequence is 0. That's an assumption here, right? All right, so this is our n point. Now, if I want to shift this sequence towards the right by 1, let's do that. Let me see what will happen to this sequence. If I shift this sequence by 1, I'll say x of n minus 1. We know what's meant by shift. It means shifting every point towards right by 1. Because this is minus 1, this means delay the signal by 1 or delay the sequence by 1. So this will be now x of 0. This will be now x of 1. This will be x of 2. So on up to x of last point will now be x of n minus 2. Why? Because this will fall outside the limit or the duration of the signal, right? So what will be this? Let me draw it. So this will be n equal to 0. Sorry, not n equal to 0, n equal to 1. Because we are shifting every point by 1. This will be n equal to 2. This will be n equal to 3. So on, and this will be n equal to n minus 1. So the last point will be this. Now there are two problems here. Not the problems, there are two issues with the duration of the signal. First thing we said, the signal starts with n equal to 0 point. Now I don't have the values of the sequence on the left side of the sequence. So what will happen? So if I assume that is 0, so I can bring that 0 here. One more thing. The last point of this sequence is this, and this point falls outside the limit or the duration of the sequence. That's equal to n minus 1 here. So that is gone here, right? So to keep the length of the sequence equal to n, what we do, we have one more shift. That's referred as a circular shift of the sequence. Now what we do in the circular shift, whatever point falls beyond outside this duration of the sequence, we bring that at the front of the signal, means at the beginning of the signal. So the first point of the signal will now be x of n minus 1, and this is n equal to 0 point. So this is n equal to 0 point. So we have kept the length of the sequence equal to n here. Again, the length is here equal to n points. So this is n point duration signal. How we do that? We wrap the point that falls outside the limit of this sequence at the beginning. And this is referred as the circular shift of the sequence, and we denote it by a special symbol or a special name like this. This is how circular shift is denoted. All right. So let me take an example to illustrate this concept further. So let's suppose we have a sequence x of n. So let's suppose x of n is 1, 2, 2, and 0. So this is our sequence. Now first let's illustrate the time points. Means this is n equal to 0 point, this is n equal to 1 point, this is n equal to 2 point, this is n equal to 3. That's n minus 4. So this is a 4-point sequence. You can check this is a 4-point sequence. So the last time point will be n equal to 3. Now if I shift this sequence, so let's shift this sequence by 1. So we say x of n minus 1. We are shifting every sample point towards right by 1. So this will be 1, 2, 2, and you can see this falls outside this limit. So this will be n equal to 1 now. This will be n equal to 2. This will be n equal to 3. You can see the last limit was here. The last value of n, small n, is equal to 3. So that falls outside this limit. So what we do in this circular shift, we bring that at the front. So we bring that here and we say this is now n equal to 0. Alright, and this is therefore as the circular shift and is denoted by something like this. So this will be, if we write this, this will be x of n minus 1. So this is the circular shift of 4-point sequence. Alright. So circular shift means simply wrapping the last point that falls outside the duration of this sequence at the beginning. Now, if I say circular shift by 2, so if I say x of n minus 2, okay, so this means circular shift of a 4-point sequence by 2 sample points. So circular shift of this sequence. So shifting every sample point towards right by 2. So this will be 1, 2. So this will be the last point now. First, this one will fall outside the limit. So this will come here. Then this one will fall. So this will come here. Right? And this is n equal to 0 point. Let me use a different. This is n equal to 1. Please pay attention. N equal to 2. And this is n equal to 3. You can say first to give a circular shift towards right by one sample. First, this will fall outside. So you will have this sequence. Then give one more shift to this sequence towards right. That will be x of n minus 2. And this will now fall. So this will come at the beginning. All right. Now, this is one way to illustrate the circular shift. Now, the same concept can be illustrated. Let's suppose we arrange the sample points on a circle. So let's suppose we have a circle and we'll arrange these sample points on this circle. So this is our x of 0. You can arrange the terms by either arranging the terms in counterclockwise fashion or clockwise fashion. This is your choice. So if this is x of 0, suppose this is x of 1, this is x of 2, and this is x of 3. Now let's write the terms also. So this is 1, 2, 2, and 0. Right? So we are arranging the terms on a circle. Now circular shift by 1. In whatever fashion you have arranged the terms, give the shift in the same direction. So if you are arranging the terms here counterclockwise, give the shift in the same direction. Now what I mean by this, so let me draw a circle first. Circular shift of 1 means this. Circular shift of 1 means this. So x of 0 will now shift towards this. This will be x of 1. This will remember your point origin starts at this location. Let me call it A. Your origin is still fixed here. So remember, you are not changing the origin. You are only shifting the points on this circle. So the origin, you will start reading the points again from this point. That's meant by this origin. Origin means your n equal to 0 point will again be located there. So every point is shifted towards right by one sample. So x of 0 will move from this to this. X of 1 will move to this, x of 2 will move to this, x of 3 will move to this. That's what I'm doing in the shift points on. So this is x of 3 now. Now write the values. Now write the values also. Let me use this marker. So this is x of 3 is 0. This is 1, 2, and 2. You can see this is same as. Now read the points. This is 0. Again, this is the origin point. Please remember this. We are start reading the values from this. This is 1, 2, and 2. You can see this is same as x of n minus 1 of 2. So this is the first step. Now if you want to compute x of n minus 1, sorry, x of n minus 2 of this 4-point sequence, give one more shift to this, or shift to this twice, directly this twice, or you can give one more shift to this. Let's do that. Let me do that. So this is our circle. Our sequence is this, and our origin is here. We call it A point, so that origin remains fixed there. This is x of 1, this is x of 2, this is x of 3. You can write the values as well here for this example. So now I'm shifting this by 2 sample points. First I will give one shift. So I will give one shift. Then I will arrange the terms. So again, my starting point is here. When I read the values, I will start from there. So this will be x of 3. Every point will move towards right by 1. This is x of 0, this is x of 1, and this is x of 2. So if you write the values also, then give one more shift to it. So give one more shift to it. So let me know the values now. So shifting this one more time. So this is our again starting point. Starting point in what sense? Means we'll start reading the values from this. X of 3, x of 1, and x of 0. Now you can write the values. This is 2, 0, 1, and 2. You can, so the x of, this is x of n minus 1 of 4-point sequence. This you can start reading the value like this. Start from this. Your first point, second point, third point, fourth point. I'm arranging the terms counterclockwise. Please pay attention. I'm arranging the, you can also arrange the terms clockwise fashion. So this is your sure. So this will be 2, 0, 1, and 2. So this is n equal to 0. So this is n equal to 0. Alright. So this is how we obtain the circular shape using a circle. Right? Alright. Now, is there any other way to compute the circular shape of a sequence? Is there any other way? There is one more way. We can use the linear translation or the linear shift that we have already learned to compute this circular shift or to do this circular shift. And that's referred as the periodic extension of the sequence. And that is referred as the by doing the periodic extension of x of n. Now, how do we obtain the periodic extension of a sequence? And let me take the same example. Let's suppose x of n is same as x of 0, x of 1, x of 2, and x of 3. And let's take that example that we have already done here. Let me write the values. So this was 1, 2, 1, 0. So this is our sequence. Now what we will do, so this is our n equal to 0 point in the original sequence. We'll extend this sequence on both sides, means on negative side as well as on the positive side. So we'll have an infinite duration of this sequence to relate it with a linear shift. So 1, 2, 2, and 0. This is my original sequence. Now I will expand this on the both sides. So I will extend this both sides. So I will have a periodic repetition of the sequence. That's why this is not n equal to 0 point. This is n equal to 0 point. So I'm extending this sequence on both sides. So, and same thing we will do on the right hand side. Sorry, left hand side. So now we have an infinite duration of the sequence, and we call this as the periodic extension of the sequence. We write it xp of n. What is xp of n? Is the periodic extension of x of n, right? On both sides. Now what we'll do, we will give a linear shift to this sequence by 1. What will happen to this? Means shifting every sample point towards right by one sample point, right? So let me start with this. So every sample point will shift to right. So 0, 1, 2, 2, 0. Then it will be 1, 2, 2, and 0. 1, 2, 2, and 0. 1, 2, 0. And shifting every sample point towards right by 1. This is 2, 2, 1, 0, 2, 2, and 1. And now our origin is this. I hope I'm right. So our n equal to 0 point is this. I have shifted every sample point of this x of p towards side by 1. Now what we'll do, we'll truncate this. So we'll truncate this and retain only the first 4 points of the sequence. These are my first 4 points because my original sequence has 4-point length. inside the original sequence. So what is the sequence equal? If I write this will be 0, 1, 2, and 3. And compare this with the circular shift that you obtained here. This isn't this the circular shift of 1? Same, exactly same. Have a look at this. And this is actually x of n minus 1 of this program. So circular shift of this sequence. So in other words, in potential, we can obtain the circular shift also by shifting a periodic extension of the original sequence by that amount. Here we wanted the circular shift by 1, means we can periodically expand the signal on both sides, then do the shift of that periodic expansion, and that will give us the circular shift. All right. So let me sum up this. What I said in this. As I said, the operation of circular convolution can be thought of as wrapping the first point that we learned. The part that falls outside the region of interest what do you mean by region of interest? Means the limit. Here the limit is n equal to 3, means last point is n equal to 3. That's the region of interest. Means our sequence varies from 0 to 3, right? That's the region of interest. Around the front of the sequence, so we bring back that around the front of the sequence, means whatever part falls outside this region of interest or the limit of that sequence, we bring that at the front of the sequence, right? Or the same way, the one that we did in the periodic extension, or the equivalently we can say just a straight translation, straight translation of its periodic extension. Periodic extension. So you can obtain the this circular shift two ways. Either you the point when you shift the sequence towards right, and some part will fall outside of the limit of the limit of duration of the sequence, then you bring back that part at the front. That will do the circular shift. Or equivalently, first you periodically expand the signal on both sides, then you give a linear shift of that periodic extension, and that will give you the this circular shift also, right? So that will give you the circular shift. Now, here is an assignment for you guys. Please do these examples. Try these examples. And the first x of n is 1020. So expand this and give a learn different circular shift. Please learn x of n minus 1 of this 4-point sequence. Compute x of n minus 2 of this 4-point sequence. X of n minus 3 of this 4-point sequence, and x of n minus 4 of this 4-point sequence. This will tell you an important yes, this will be an important result of this one. Right? So next example that you will do, and you will repeat this or you will do this. Do the same for this. Right? So learn it using this periodic extension, as well as if you are in the terms on the circle, or if you do it in your mind intuitively. How do we add in the terms? All right. So how do we read this notation? Now I said x of n minus m of n point sequence. How do we read this? This is read out like this. This means the circular shift of by m sample points modulo n. This is how this is read. This is read like circular shift of x of n modulo n, modulo m, modulo capital M, and this is the shift. This is the shift. Okay, this is how we read this operation. This operation. So this is read as x of n minus m modulo n. All right. Okay, this is how done. This is the notation that is used in the literature. All right. Now, before I end this session, one very important point I make: the DFT of a circularly shifted sequence. What is the DFT of circularly shifted sequence? So we say our circular shifted sequence is x of n minus m modulo n. We read it like this. Then if we take the DFT of this, what is the DFT of this sequence? What is the DFT of this? And the DFT of this is simply Wn raised power km. Now you know what is Wn. This is quadratic factor x of t. What is k? X of k. X of where x of k is the DFT of x of where x of k is the DFT of. This is very important property of this DFT. This is very important property of the DFT of a circular shifted sequence gets multiplied by the quadratic factor raised power km and the original DFT of the sequence. Original DFT of the sequence. Alright, this is very important for circular convolution when we do the circular convolution. Alright, let me end the session here. Please practice it. You'll get the terms.